Okay, so on this quiz, we're doing some probability rules, and our first question focuses on what age groups use social networking sites. So our first question here is, suppose one subject from this study was selected at random. Find the probability that the selected subject preferred Twitter. So the probability of Twitter, which I'm going to write as P of T, is going to be our subjects who prefer Twitter. So you'll notice I've circled 244. That's our subjects that prefer Twitter, divided by the whole sample space. So in this case, that's 768. So then we calculate that out, round it off, and we come up with 0.318 for A. Now, for B, we are asked the probability that the selected subject preferred Twitter, given that he or she was in the 45 to 64 age group. So we can write that like this, or probability of preferring Twitter given the 45 to 64-year-old age group. Of course, this is going to be those who preferred Twitter at 45 to 64, I've circled that, over all of those in the 45 to 64-year-old age group. So that would be 81 over 290, which, when we punch it into the calculator, comes out at about 0.279. So there's our probability for B. For part C, we're asking if the events preferred Twitter and age group 45 to 64 are independent. And we're asked to explain this. To test this, we're going to see if the probability of preferring Twitter matches the probability of preferring Twitter given that the subject is in the age group 45 to 64. When we plug in those probabilities, and I'm going to change the color here just from green to red because I noticed that green's a little hard to read. But we can see that obviously the probabilities from A and B do not match because 0.318 certainly is not equal to 0.279. So our conclusion is going to be no, because the probability of preferring Twitter does not match the probability of preferring Twitter given that you are in the 45 to 64 age group. This last one really hinges on the definition of mutually exclusive. For events to be mutually exclusive, events A and B, they cannot occur at the same time, meaning that if event A occurs, there's no possibility that event B also occurs. So what we're asked to do is look and see if preferred Twitter can ever occur when age group 45 to 64 also occurs. And we actually see up here that 81 subjects, both events occur. They are 45 to 64 and they prefer Twitter. Therefore, we can say no, because 81 subjects prefer Twitter and are in the 45 to 64 age group. For part E, we're asked if a random sample of 2 subjects were selected, what's the probability that neither preferred Twitter? For this, you'll have to remember that the multiplication rule tells us that the probability of A and B equals the probability of A times the probability of B. Now, of course, in this case, the probability of A happening is those who do not prefer Twitter divided by all the subjects. In other words, the 524 that do not prefer Twitter divided by the 768 in the sample. Things become slightly more complicated when it comes to event B, which is choosing the second subject. The challenge is now we've removed one person who does not prefer Twitter, and we've removed one person from the whole sample because we've pulled one person out for that first part of the sample. So our probability would look like this, which is 523 divided by 767. Notice that we've pulled out one subject from the total sample space, and we've also subtracted one that did not like Twitter, because of course that was the subject that we chose in the first event. When we multiply all this out, that comes out as 0.465. And that is the probability that neither of the subjects we select prefer Twitter. Next up, we're talking about Ramon driving or riding his bike to work. And we're asked to consider that we choose a random workday. And the following table gives us the probabilities of several events. Now, something important to notice about this table right off the bat is there's a lot of probabilities or events that are missing. We notice that those probabilities only add up to 0.55. So even if they are all mutually exclusive, we know that there are other events that could possibly happen that are not in this table. So part A asks us to consider the probability that Ramon is late for work, given that he drives. We're going to therefore be needing to find P of L given D, and the formula for that is P of L and D divided by P of D. Fortunately, we have both of those, so we can just plug them straight into the formula. So as you can see, we've plugged those in, and now we put them into a calculator, or we just simplify, and we come up with 1/4 or 0.25 or 25%, all of which would be fine answers. Next up, we're asked to find the probability that Ramon is not late for work, given that he drives. Of course, if he drives, he must either be late for work or not late for work, meaning that we can set up the following equation. Probability of not late, given that he drives, equals 1 minus the probability that he is late, given that he drives, since 1 must be the total probability of him being either not late or late, given that he does drive. So now we can simply plug that number in, and of course we can see that 1 minus the 0.25 from part A gives us 0.75 for part B. It's useful that we found those probabilities because the next thing we have to do is draw a tree diagram. So I'm just going to sketch the full tree diagram first, and then we'll fill in the probabilities. And of course you can see that out of all the times Ramon goes to work, we can break it into the times he drives and the times he bikes, and then from those into late and not late for each one. Now, of course, we know that he drives to work 20% of the time. And from this, since we know that he always goes to work, or at least we assume so, we know that he must bike to work 80% of the time. So I filled in the bikes to work as 0.8. Of course, after this, we have some conditional probabilities already. We know that 25% of the time when he drives, he is late for work. We found that in part A, so we can fill that in. And in part B, we found that based on part A, we know that when he drives, he is not late 75% of the time, so we can fill that in as well. So those are now in. We have 0.25 and 0.75. Now, if he bikes, we're looking for the probability that he is late to work given that he bikes. And of course, we can actually see that this is given in that table up there. Late for work given he bikes is 0.3. So we can add that in as well. And of course, finally, we need to add in the probability that he is not late given that he bikes. We already know that 0.3 of the time that he bikes, 30% of the time that he bikes, he is late, which means that 70% of the time that he bikes, he is not late. Finally, we need to look for the probability that Ramon drove to work, given that he is late. And for here, we're going to need to use our Bayesian statistics again. So first of all, let's write out what we're actually looking for, which is the probability that he drove given that he is late. Now, this is kind of backwards from what we normally find, which is what makes it hard. The formula to get this is as follows: P of L and D, meaning P of being late and driving, divided by probability of being late, which is all the times that he is late. So I'll fill those in now. So this is a doozy. This is the probability that he is late and driving is 0.2 times 0.25, and you can actually see this in the top line of that chart. That's going to be driving and late. Then on the bottom we have driving and late plus biking and late, which of course is, and I'll circle this too, 0.8 times 0.3. So that gives our total lateness. Now we simply have to divide, we have to multiply out and divide. And when we do all that, we come up with approximately 0.172. So that, again, is quiz 5.3b. This is kind of our heavy focus on probability rules. And hopefully that helped you maybe understand some of the questions on the quiz a little better, and maybe it will help you study later on down the course. This has been Lunar Math with Mr. Moon, and I hope to see you guys again soon.